All right, we're we're switching gears. Um, After a really solid, nearly 3 weeks of talking about chemical reactions from a standpoint of speed, and then from reversibility, and all the fun equilibrium directions that we took it in the past two chapters. We're going to go to a more concrete discussion, looking at chemical reactions from a different perspective, let's call it. And so this chapter and the next chapter are in a lot of ways paired together, and your third exam will pair them together. And in a lot of ways it'll make sense, and you'll see when we get there, because ultimately electrochemistry, which is what the next unit is a large scale application of chemical thermodynamics. And so we're going to talk about thermodynamics for today and for tomorrow. And we'll start by just, you can see, one of the things that is going to jump out to you about this chapter and the next is how short they are by comparison. Thermodynamics is basically two concepts: entropy and free energy. Today we're going to talk about entropy. Tomorrow we're going to talk about free energy. And we'll see that from an electrochemistry standpoint, kind of similar. We'll talk about redox reactions. We'll talk about electrical flow, direction of electron flow, which comes back to redox. And then we'll talk about some applications of it as well. But what we have to understand is that this change also comes with a change in mindset. When we started this semester off, we talked about the idea of reaction speed, the idea of a rate constant giving us the speed of the reaction, how fast the reaction goes to completion, or how fast the reaction goes in general. Thermodynamics isn't concerned with speed. Thermodynamics is instead concerned with direction and extent. And if those terms sound a little bit familiar, well, our equilibrium constant gave us a little bit of ideas of direction and extent as well. But they were ultimately couched inside the idea of a reversible reaction. We're going to get into processes that are not necessarily reversible anymore, but still can be talked about in terms of direction and extent. And the term we're going to use for this is spontaneity. We're going to describe things as either being spontaneous or non-spontaneous. And one thing that we have to be careful about with the terms is that the term spontaneous does not refer to the kind of average everyday life definition of spontaneous. When we talk about spontaneity in a person, we talk about their ability to be random, unpredictable, kind of going off by the seat of their pants, randomly changing directions without warning. In chemistry and in thermodynamics, what we're talking about is a process that happens without any interference. So something that is going to happen on its own naturally. That's what it means to be spontaneous. And there are lots of different directions, lots of different ways that we can view that kind of spontaneity. For example, I am holding this marker here at my face. But if I were to let go of this marker, we could pretty accurately predict where the marker is going to go. The act of gravity on this object is one that happens without any kind of outside interference. Unless you consider the gravity itself, but that's a completely different conversation. Nonetheless, there are chemical and physical processes that we can observe that will happen naturally on their own without us doing anything about it. If I go down to Huck's and buy a bag of ice and leave it in the middle of the floor, I should not expect to come back tomorrow and see that bag of ice still sitting there. Why not? Well, we know that at this particular temperature, water doesn't exist as a solid, it exists as a liquid. So what's going to happen to all of that ice? It's eventually going to melt. The spontaneous process of melting at a given temperature is going to happen without any kind of outside interference. The only way that we're going to keep that ice as ice is if we introduce some kind of prevailing force upon it to keep it in the solid phase, like, say, exerting a ton of pressure on it, locking in some kind of a jar, pumping it full of some sort of atmospheric gas to raise the pressure so that, if you remember phase diagrams from 105, we can push water into its solid phase contingent. The other thing that we should note about spontaneous processes is that they are unidirectional. There is no equilibrium associated with spontaneity. They happen in one direction and one direction only. So if we're going to talk about spontaneous processes, we also have to talk about non-spontaneous processes, the opposite. So things like this. I dropped this marker and it fell to the desk. That was a spontaneous process based on potential energy and position. Now, what is the likelihood that this marker is going to, on its own, leap off of the table and come back into my hand? I'll wait. It's not. That's the definition of a non-spontaneous process. So processes that can occur will happen spontaneously. Those that will not are non-spontaneous. Other examples. Universal expansion of gases. I put a sample of gas into a room, it fills the room with whatever gas it is. That's a spontaneous process. The gas, through random motion, is not going to automatically segregate itself from the rest of the gases in the room and create a pocket of nitrogen over there and a pocket of carbon dioxide over there and a pocket of oxygen over there. That's not a spontaneous process. We're not going to find this glass of water turning into ice just sitting here on the counter. It's not going to happen. It's not a spontaneous process. So with this in mind, let's go ahead to our first question of the chapter here. And I've got 3 questions here. 3 processes. I want you to identify them as being spontaneous, non-spontaneous, or at equilibrium. So if it's spontaneous as written, mark it that way. If it's not spontaneous as written, but rather in the reverse, mark it that way. If it's at equilibrium, meaning that both processes are happening, both the forward and the reverse, then take it that way as well. So I'm going to open all 3 here at once. All right, so let's look at this first one. We have water at 40 degrees Celsius. We add a 150 degree piece of copper to it. Is the water going to get hotter? Now, all of you have said that is spontaneous as written, and you are all correct. All right, let's look at this next one. I have water at room temperature, and it is decomposing into hydrogen and oxygen. Ooh, okay, we're split. Okay, what kinds of processes can water at room temperature undergo? Undergo evaporation. Does evaporation also decompose the water into its elements? Evaporation is merely a phase change. We go from water in the liquid phase to water in the vapor phase. There's no decomposition that's taking place. This reaction cannot go as written. The only way we can get water to decompose into hydrogen and oxygen is we have to literally shock it with electricity. We have to hit it with enough force of electrical weight to force those bonds to break and to reform as hydrogen and oxygen. So the question you might be asking is, well, how is it spontaneous in the reverse? Well, if I take hydrogen and oxygen gases at room temperature, I can get them to form water vapor. All I need is enough activation energy to get the party started. And this is basically what you see when a hydrogen balloon explodes. The flame or the source provides the activation energy. The hydrogen and the oxygen do the rest. And they can do it at room temperature here. We don't need to raise it up to 500 Celsius or something like that to get it to work. So the correct answer here is spontaneous in reverse. All right, last one. Benzene is condensing to liquid. So we have benzene vapor condensing to liquid at the normal boiling point, which is 80.1 degrees Celsius at 1 atmosphere of pressure. Okay, we're even more divided. Okay, correct answer here is at equilibrium. The key point here is we have to understand by definition what phase changes are. Phase changes, so long as we stay at those conditions, think about the phase diagrams. At those intersection points, we have both phases present at the same time. So long as we maintain those conditions, we will see an equilibrium of the liquid and the vapor phase. Now, the question that you might be having is, well, wait a second. When I boil water on my stove, if I just leave it there, eventually all the water goes away. Isn't that a sign that a phase change is one directional? And there are two problems with that particular analogy. One of them is that if you're keeping it on your stove, you're continually adding heat to the system, which, if it was just being done to keep it at 80.1 degrees Celsius, that would be fine. But chances are pretty good that if you measure the temperature of the bottom of your pot, it's greater than the 100 degrees Celsius that would be necessary to boil water. And the second thing is you're not maintaining that 1 atmosphere of pressure. Because if you're boiling in an open container, what's the first thing that steam does? It goes away. Think about your Le Chatelier's principle here. If I have an equilibrium system where the product continues to float away, how is the equilibrium going to shift? It's going to shift to make more product, to replace the product that is leaving. So the issue here is a matter of containment. To be truly at equilibrium, we would have to cap the system to maintain that constant temperature and pressure. And if we were to do so, what we would find is that at that temperature and pressure, we would see an interconversion between the two phases where one does not necessarily replace the other. We'll get the true definition of equilibrium. Liquid's turning into gas, gas is turning into liquid. The rates of each reaction are equal, and such, since they're equal in opposite directions, we would see no net change in amount for either side. So just to recap, first one was spontaneous in the forward direction. The second was spontaneous in the reverse. And the third one was at equilibrium. Okay, so to get into a better, more concrete conversation about thermodynamics and, more importantly, entropy, we need to start thinking about and looking at molecular motion a little bit more finely. And one of the things that we need to start to look at and start to think about is, are there different kinds of molecular motion? And the answer to that question is yes. There are, in fact, 3 different modes of molecular motion. Now, the first one, the one that we probably think of the most, is what we would call translational motion. Translational motion is just the ability for that molecule to move around in its space. And if we think about things in terms of kind of a Cartesian kind of axis way, there are 3 different dimensions that we can have translational motion in. The X, the Y, and the Z. And so we would call those 3 different degrees of freedom to describe the motion of a particular molecule. So there are 3 translational modes of freedom. But what we haven't considered, at least not yet, is that for things that have chemical bonds, there are other kinds of modes of motion that we have not yet considered. And so we're being asked to consider, well, what if I have something like hydrogen, where I've got two hydrogens that are bonded together? Well, in addition to the three translational modes, we would also have two rotational modes. We could rotate this way, but we could also rotate about the axis. So there would be two rotational degrees of freedom. And in addition, that one bond would have the ability to vibrate. And so we would talk about having a vibrational mode as well. So in going from an atomic sample like helium, where all it has are the three translational modes, a simple bonded molecule like hydrogen has more. And if we up the complexity of our molecule, what we'll see is that there are even more degrees of freedom to discuss. Now, why is this important? Well, the reason this is important is because what we're going to start getting into is the concept of entropy. And entropy, in a lot of ways, is about the ability to take kinetic energy and manifest it in different ways. The more ways that you can take that kinetic energy and redistribute it and reconfigure it and put it out in different kinds of modes, the more entropy that the system that you're looking at will have, which will translate to more entropy. So we start with this idea of degrees of freedom, just as an understanding that this is one of the ways that we can kind of start to begin that conversation. What this ultimately leads us to are discussions of what are called microstates. Now, microstates are unique arrangements of energy within a system. Now, the system that we're describing here is not necessarily a reaction or a chemical reaction process, but it could just be the state of affairs. And so what we talk about are macrostates. Macrostates are the measured properties of a particular system. So if I'm describing a particular system, the macro state would be describing, okay, what is the temperature of that system? What's the pressure of that system? What kind of kinetic energy, momentum, number of atoms, different kinds of molecules? What's present in that system at that given time? That's what a macro state is. A micro state would be within that macro state system, how many different unique arrangements of energy are possible? And so the discussion that we are going to get into here is going to follow up with the idea of, okay, just how many microstates can be used to describe this macro state? And that's going to lead us into a discussion of entropy. So let's take on an example that should at least be somewhat common to us. Let's say that we are throwing dice. Relatively simple probability problem. I have two dice. There are a total of 11 different outcomes. I can't throw two dice and get a total combination of one. But I can get any number between 2 and 12. So those numbers, 2 through 12, those are the macro states. Those are the possible combinations that I can get in terms of value. So if you're playing Monopoly, if you're playing, um, you know, any other kind of dice game, you know that getting a 2 or getting a 12, those are harder things to get. And so we can see that from a standpoint of here are all the possible common macro states, the possibility of getting a microstate of or a macro state of 7 is the highest. Why is it the highest? Because there are 6 unique ways to get 7. You can get 1 and 6, you can get 6 and 1. You can get 2 and 5, you can get 5 and 2. You can get 3 and 4, you can get 4 and 3. Each one of those dice combinations, those 6, are a microstate, a different combination of dice that will get you to that macro state, that total score of 7. And you can see that it cascades down from there. Next most common is 6 and 8. And you see that there are 5 different combinations of 6, 5 different combinations of 8. And so on and so on and so on, all the way down to snake eyes, 1 on each dice. Microstate of 2, there's only 1 combination to get that. And 12, there's only 1 combination to get that as well. Both have to be 6. So with a combination of just simple dice, what we can see is that, okay, we got 11 different macro states and a whole bunch of micro states just off of 2 dice and what those 2 dice mean in terms of their combinations with each other. Now let's bring that out to a chemical system where we have millions upon billions of atoms, of molecules in a given sample. And what we're going to quickly come to the realization is that it is pretty much impossible to count and describe all of the different microstates in a chemical system. If I'm looking at the chemical system of even just something like a mole of hydrogen gas in a balloon, the fact that there are Avogadro's number of hydrogen molecules in that balloon is enough to create so many different microstates that it would be impossible to count them, let alone try to describe each one. But what the Boltzmann equation allows us to do is it allows us to define a relationship between the number of microstates that exist in a particular macrostate to the entropy of that system. And the equation for that is relatively simple. Entropy, S, is equal to the Boltzmann constant, so K sub B, which is 1.381 times 10 to the negative 23rd joules per mole Kelvin, multiplied by the natural log of W, W being the number of microstates. The key idea here is this. The more microstates that a particular system has, the greater its entropy is going to be. And the greater the entropy, the more likely it is that we're going to see it happen. So putting this into our idea of the dice game that we just saw. If I'm evaluating the macro state of 7, 7 has the highest probability of being achieved. That's also because there are the most combinations of dice that will yield 7. The more microstates we introduce, the larger the entropy is going to be overall. Now, taking Boltzmann's equation to its furthest limit, we know that if there is just one microstate for a particular system, natural log of 1 is 0. 0 times the Boltzmann constant is 0. This leads us to what is called the third law of thermodynamics. Now, in your brain, you might be saying to yourself, okay, I think I remember the first law of thermodynamics. And you do. We covered it in Chem 1. It's energy cannot be created or destroyed, the law of conservation of energy. Now, we haven't talked about the second law of thermodynamics yet. Why are we skipping to the third one? Well, because the third one's actually going to help us to kind of establish why the second one makes sense. So the third law of thermodynamics is this. If I have a system that has only one microstate, its entropy is equal to 0. Now, what does it take to have only one microstate? Well, I have to have a perfect crystal, meaning that it is perfectly ordered. There is no chance of having any kind of imperfection in terms of its stacking, in terms of its packing, in terms of its arrangement. Nothing is out of place. It is perfectly pure. And this is the most important part, it has to be at absolute 0. Why at absolute 0? Well, because we know that at absolute 0, kinetic energy ceases, which means I would have no translational energy, no vibrational energy, no rotational energy. So I'd have none of the energy motion-based degrees of freedom to work about, and I would have none of the configuration modes of entropy to worry about either. The reason why the third law of thermodynamics is so important is that because it establishes for us the baseline. Okay, what does 0 entropy look like? And from that establishment of 0 entropy, we can start to build up, based on relative terms, every other kind of entropy unit that exists. This is a very similar argument to why we have the Kelvin scale. Why does the Kelvin scale ultimately make sense? Well, because it establishes, well, what does 0 energy look like? On the Kelvin scale, that's T equals 0. Every other energy, every other temperature can be measured based off of that absolute 0 mark. So just like every other temperature can be established off of absolute 0, so can every entropy be measured off of 0 entropy, absolute 0 for that entropy scale. And what this allows us to do is it allows us to define everything else. So I'm going to take you back here. We've been referencing these appendix tables relatively often here, especially over the past few days. And I want to take you back to the front now. Now, your textbook in Top Hat has an abridged version of this in Appendix 4. So if you go to the 106 textbook in Top Hat and you look at Appendix 4, you'll see thermodynamic table values like this, but not nearly as many. Now, one thing I will tell you is that for your active problems, I would defer to whatever text resource that they give, just because chances are that there's going to be a little bit of variability from resource to resource, depending upon which reference table they ultimately used and when that reference table was published. But you can see here that there are 3 columns on this table. Delta H being the first one, enthalpy. That was something that we dealt with in Chem 105. The last column here, S, is the standard molar entropy for every given substance in the table. Those standard molar entropies are set and measured at 298 Kelvin and 1 atmosphere of pressure. But the values themselves are set to, well, based on absolute zero, based upon that third law of thermodynamics. Now, we'll talk about the middle column, G, tomorrow. That's for Gibbs free energy. But we can start to establish here, okay, there's a baseline, there's a place where we're starting that we're going to use to try and make sense of it all. So we want to take a quick note here. A lot of resources, a lot of textbooks will try to frame entropy as a matter of the measurement of disorder in a system. And in a lot of cases, it makes sense in that way. But one thing that we've got to be really cautious of, for a lot of chemical systems, disorder makes sense. I can look at, okay, these chairs over here are all lined up in these very neat columns and very much out of the way. And the chairs that you're sitting in would be joining them if it weren't for the fact that we were here every day. But let's put it in the context of kind of natural tendencies. When there are classes actually going on in this building, there is no way that those chairs are going to stay exactly where they are like that for the entire semester. And you've seen it. Take class in any of our classrooms. Over time, the desks get a little bit disjointed, things start moving around a little bit, and unless there are staff coming in here constantly to reorganize and reword them, the classroom on Friday is a little bit more jumbled up than the classroom on Monday. That's the natural order of things. We have a general tendency toward disorder, toward a lack of organization. Anyone who's ever spent more than 5 seconds in my office knows that very, very well. But disorder is not the only lens that we have to use. The more proper lens for evaluating entropy is through energy, through these ideas of microstates. That's the more proper way of doing it. I will tell you this, though. if we are trying to evaluate things from a qualitative, non-numerical standpoint, disorder does help out a lot because it's a lot easier to kind of just look at something and evaluate it in that kind of way. And so that's where we want to keep that kind of discussion is if I'm in a quick hitting kind of sense going, okay, is there going to be more entropy over here or over here? I can look at, okay, well, that's more disordered than this one. The entropy is going to be higher over there. But I can't measure disorder. I can measure entropy. And so to that end, here are some things that we can do to help us to evaluate from a trends kind of way where there is entropy and where there is not. So let's start with phase. Different phases of matter have different amounts of disorder. They have differing amounts of entropy. Solids tend to have the lowest amount of entropy. Gases tend to have the highest amount of entropy. Why is this the case? Well, in addition to usually having lower kinetic energy, solids are relatively rigid in their structure. And that rigidity in their structure is going to limit their translational degrees of freedom. It's going to limit their overall degrees of freedom. If you're locked into place, that means that you're not going to be able to move around nearly as much. Why are gases the highest in entropy usually? Well, because they have neither shape nor volume to constrain them, they are going to have the most degrees of freedom. And as a result of having the most degrees of freedom, they're going to have the greatest entropy because they're going to have the most microstates. Liquids kind of fit in that space in between. They have more freedom of motion than solids do, but not nearly as much as gases do. So they have more degrees of freedom than solids, so we expect them to have higher entropies than solids, but not nearly as much as gases. They're still constrained by volume. Gases have an undefined volume. They take up whatever container they're in. Liquids will only take up the amount of volume that they are. So that's one trend that we can look at. And that, honestly, if we're evaluating things from like a disorder standpoint, this is the one that we usually point to the most. Now, before we move any further, I want to just make you aware of some terms that we used in Chem 105 and make sure that we remember these definitions again. So the difference between an open system, a closed system, and an isolated system. So in an open system, matter and energy are free to flow in and out of the system and go between the system and the surroundings. The definitions that we are being given here involving 3 different cups of coffee are a pretty good one. So an open system, like an open cup, matter and energy are able to freely flow in both directions. In a closed system, matter is contained. So here I have a travel coffee cup that actually has a lid. And what you will find, and put out any kind of system like this, if you go to Impressed here in town, or if you go to Starbucks or Dunkin', or pick your favorite coffee place, and they give you a paper cup with a lid on it, you've got yourself a closed system. The system is open as soon as you open up the lid and take a drink out of it. But as soon as you put that lid back on, it's a closed system. Now, anybody who's anybody would know that your hot coffee, or your cold coffee for that matter, is only going to stay hot or cold for a finite period of time. And the reason why is because it is a closed system. Matter isn't getting out, matter is stuck. Matter is stuck in the system. But energy, that can flow in and out of the system. So, if you put that same cup of coffee in your car during a summer day, your iced coffee turns to water and your hot coffee stays relatively warm. If you put that cup into a cold area, bring it inside to the air conditioning, the cold coffee stays cool for a while, eventually comes to room temperature. The hot coffee gets cold relatively quickly. An isolated system, both matter and energy are trapped inside of it. A well-insulated thermos is a good example of this. So I've got matter and energy, and they're both contained. Now, there are other examples of systems that we can consider relatively isolated. Um, most of the high quality water bottles that exist now, the Stanleys and some of the other ones, the ones that can keep ice for extended periods of time, Yeti coolers, other similar brands. None of them are truly isolated. That's kind of an impossibility, but certainly they slow down the energy transfer enough that it's in the margins that we just don't care. Okay, so with this idea of phases in mind, let's predict whether we're going to see an increase or a decrease in entropy for each of these processes. Okay, so in A, I've got a gas and a gas turning into a solid. So from a mere idea of energy and disorder, two gases are going to have way more degrees of freedom than this solid is. Entropy is going down. Another way of saying this is that our change in entropy is negative. Remember, uppercase Greek letter delta indicates change. We saw this with enthalpy in the thermochemistry unit last semester. Um, we can also see it here used to describe entropy as well. All right. In this case, we have a solid being dissolved in water to make a solution. So, thing that we have to remember, okay, solid, again, rigid crystal, everything's on top of each other, not very much degrees of freedom of motion. In solution, each one of those individual molecules of sugar is going to get surrounded by water molecules and move around. I went from solid phase, not a whole lot of movement, to liquid phase, aqueous phase, where we are going to have at least some freedom of motion. We're also going to have what is called basically entropy of dissolving, where instead of being in an ordered crystal with only sugar molecules, now I've got sugar with water molecules. The mere act of having a second molecule present, that is a different kind, is going to increase disorder, increase entropy that way. So our entropy is going to go up. Delta S would be positive in this case. In this third one, we've got a gas and a gas turning into gas. Ooh. Okay. In this case, we can't rely solely on phases, but we can look at numbers of gas molecules. So I have 3 gas on this side versus 2 gas on this side. More gas molecules would mean more different microstates because I'll have more different combinations that I can play. So in this case, my entropy is going to go down. Delta S would be negative. All right. Any questions with that guided example there? All right. I want you to try this on your own. And this will be the last thing. We'll take a break. Okay, so structure of the question is a little bit different than what's printed on the slide. I've given you all 4 of those equations. Click on as many of them as is necessary to click on all of them where delta S would be positive. So where is entropy increasing in this case? All right, so we see water going from a liquid to a gas. So we would expect an increase in entropy that way. Here we've got a liquid, or we've got solutions of silver and chloride turning into a solid. Solids are not good for entropy. Here we have a solid and a gas turning into a solid. Here we have gases turning into other gases, but just like we saw in the previous example, we have 3 gases turning into 2 gases. So we are decreasing the variety and number of our gas molecules. That should lead to a decline as well. So only the first one should be correct. And that's exactly what you said. Good job. Okay, let's take a break here. And when we come back, we will talk about the second law of thermodynamics, and we'll also start to get into some calculations.